Good morning or good afternoon, depending on where you are at. My name is Atarad Azizin Amini, Director of the ABC-UTC at Florida International University. We had a very successful 2021 virtual ABC conference, and we are delighted to say that we are as anxious as you are to get back to having a face-to-face meeting. I know everybody's getting really tired of these virtual meetings and so on. So the conference in December 2022 is going to be face-to-face in Miami, Florida. Go ahead and submit your abstract if, on any project. This is a back to normal. The 2021 was related to having an international focus. 2022 is basically back to similar conferences we had, like 2014, 15, 17, and 2019. There are lots of opportunities for exhibit, sponsorships, and so on. More than 30 state DOTs have co-sponsored basically the conference. I also wanted to mention one item before I turn it to Mary Lou. Everyone knows that last Friday, the Biden administration released $27.5 billion for the bridge projects. And at ABC-UTC, I've sent the emails to many state DOT engineers. We will be very delighted to work with you. If you're a consultant, if you're a bridge owner, and if you would like to work with ABC-UTC in some of the opportunities that are related to the new transportation bill, please send me an email. My email is very easy to find, aazizina@fyu.edu.
Our presentation today features the New Hampshire Department of Transportation's first lateral slide, the Bearcamp River Bridges Replacement Project. We'd like to thank Loretta Girard Doughty, State Bridge Engineer and Administrator of the Bureau of Bridge Design with the New Hampshire DOT, for coordinating this presentation. We're pleased to welcome our presenters, Jennifer Reczek, Project Manager and Bridge Consultant Design Chief with the New Hampshire Department of Transportation, Sam White, Project Manager and Senior Bridge Engineer with McFarland Johnson, Inc., and Jim Bowles, District Construction Engineer with the New Hampshire DOT. Jennifer?
Thank you, Mary Lou. Before we get started, I'm going to let Loretta Girard Doughty, our Bridge Design Chief Engineer here at New Hampshire DOT, say a few words, and then we'll get into the presentation.
Hi, just quickly, I wanted to thank the Florida International University for having us, and to thank everyone for participating today to view our webinar. New Hampshire is fairly new to accelerated bridge construction, and we are proud of the project and the project team for delivering the successful project. So we hope that you find this project both interesting and informative. So thank you again.
All right, well, thank you. As was mentioned, I'm the project manager here at New Hampshire DOT for the project. What many of you may not know is that I've actually been involved with the project since 2013 when I was a project engineer within the Bureau of Bridge Design. And it was during that time as a project engineer that I was working on an alternatives analysis for the project and was heavily involved in gaining the approval to move forward with the first slide. So we've broken the presentation up into 3 sections. The first part that I'll be covering is the why. In other words, other than it seemed like a fun thing to try, what factors led to the decision to use this technology. We'll also discuss some of the design considerations that were addressed during the development of the contract plans. And then finally, we'll end by stepping through how some of these considerations and the resulting designs were implemented during the construction phase. So to start off with, where is New Hampshire? For those that may not be familiar with us, we were the 9th state to join the nation, and we're located in the northern part of the 6-state region known as New England. New Hampshire is shown here in red. We're tucked between Vermont on the west and Maine to the east. We're a pretty small state. We have approximately 2,100 state-owned bridges. The Bureau of Bridge Design advertises about 15 projects per year, and of those, we average about 3 bridge replacement projects. So this bridge, or this particular project, was a pretty big one for us. It actually contained 3 bridges, two of which used the slide technology and that we'll be talking about in this presentation. This gives you a little bit of a sense of where the project is in New Hampshire. This was located in the town of Ossipee, which is in east central New Hampshire. It's located on a section of roadway where two principal arterial roads actually run concurrently. New Hampshire Route 16 runs north-south on the eastern side of the state. It's the primary roadway connecting seacoast New Hampshire and eastern Massachusetts up to the Mount Washington Valley, which is one of our premier recreation and vacation destinations. New Hampshire Route 25 runs east-west. It connects over from Portland, Maine into the Lakes region of New Hampshire, which is another popular vacation destination. The roadway within the project area was built in 1955. It has two 12-foot lanes with 4-foot shoulders and has a speed limit of 45 miles an hour. I mentioned previously that this is a big vacation area. So we have an average of 11,000 vehicles per day, but that actually varies between about 9,000 during lower times and up to 18,000 vehicles per day during peak summer traffic. This is getting a little bit closer to the project area itself. You can see the river running down the screen. Route 16 is heading kind of left to right on this page. North is to the right. These two bridges, the Bearcamp River Bridge, you can see on the left, is over the main river channel, and the Relief Bridge is about 600 feet east of that, and that provides flood relief during high periods of flow. Some other things to note about the project area: the Bearcamp River flows sort of down the page or to the east. We have a large area of wetlands and sensitive environmental communities that were located to the east of the roadway. There were utility lines located along the east side of the roadway. We had businesses on either corner here of the roadway, and these are located sort of at the fringe of the floodplain. New Hampshire Route 16 in this vicinity, this is sort of one edge of the floodplain. It's about 2,000 feet across, and then the other edge is located kind of in this diagonal. And then within the actual floodplain itself, there is a residential community of sort of summer vacation type homes, although some have been converted to permanent residences. This is an overview of the Bearcamp River Bridge. This was the former bridge. It was a 392-foot long, 5-span steel I-beam structure. As you can see in this picture, the end spans and most of spans 2 and 4 are actually located over dry land. Again, this is because under typical conditions, it is dry, but this whole area floods under heavy rainfall events or when we get heavy snowmelt. This is the original Bearcamp relief structure. This one was a 168-foot long, 4-span steel I-beam structure. This one was located on the northern side of the floodplain, providing that additional hydraulic capacity. And in the bottom right photo, you can see a little bit how the roadway is elevated up above the surrounding floodplain. This next slide gives you another indication on the bottom. This is actually the original profile from when these bridges were constructed. So you can see their close proximity and also get a sense for how that roadway is constructed up. It varies between about 10 feet and 14 feet above the surrounding grade. At the top of this slide, this is the original typical section. With the exception of the girder sizes, this was identical for both structures. They were designed sort of interestingly for the bridge people in the audience. They were designed as simple spans under dead load and continuous under live, which was a unique feature within the state of New Hampshire. They had 4 main girders with 2 smaller exterior girders under an open grate shoulder and sidewalk or curb section. So that again is a fairly unique feature, but that's part of what led to their premature failure and ultimately their replacement. So as we began our alternatives analysis and looking at the replacement, we had structured a few design considerations that I've placed here. Because of the importance of this roadway, we wanted to make sure that any temporary roadways were constructed for the 45-mile-an-hour speed limit. We wanted to maintain the roadway elevation above the 100-year flood elevation, again, because of the importance of this roadway. The temporary bridge spans needed to match the existing spans or exceed them because of their location within the floodway and because of the length of time that they would be in place. And then we also, with all of our projects, we look at trying to minimize our impacts as much as possible to abutting properties and the natural environment. So we started looking at temporary alternatives, and in the state of New Hampshire, we use the term diversion if it's an on-site rerouting of traffic. So New Hampshire's typical approach is to look at a diversion first with a temporary bridge. And we started looking at those alternatives, and then because of the temporary bridge cost and the amount of fill that would have been required to keep that temporary roadway above the 100-year flood elevation, we were basically constructing a new Route 16. And so at that point, we also evaluated permanent alignments. So we looked at some to the east. And again, this is a conceptual rendering. But on the east side, we ran into several concerns. We had that environmental community. You can see on the left-hand side of the screen that alignment actually impacted part of the old river channel. And we did run into some interesting geometric constraints with those alignments, looking at super elevation transitions on a bridge that was partially on a horizontal curve, just some unique geometries there. Then we looked at a western alignment, both for the temporary as well as permanent. On that side, again, because of the way this section of road is located between these two curves, that also led to some geometric constraints. And in this location, we actually ended up impacting businesses, which we would need to relocate. So that was not particularly desirable. And we would also have been moving the roadway closer to some of those homes, which perceived or real led to concerns about noise, potential during future flood events, that sort of thing. And so what we were finding is that this road really was in the ideal location. The geometry is pretty good, and that led to this question of, well, how do we build the bridges in the same location without that cost of temporary bridges and a diversion? And that's where the idea of doing the bridge slide came into play. So as we moved forward in that approval process, one of the big questions and things that we needed to look at was the traffic and the feasibility of, could we actually do a roadway closure in this location? So the graph that we have here was from one of our permanent counters on Route 16 in the vicinity of the project. And this just shows the very seasonal nature of our traffic in this area. So starting on the left in January, you see a little peak as people head home after the new year. Things are pretty quiet. There's a spike in February. So in New Hampshire and most of New England, our schools have a week-long February vacation and then a week-long April vacation. So we see a lot of ski traffic in that February timeframe. Then things are pretty low again, and you see the next peak at like the Memorial Day timeframe, spiking up the 4th of July weekend. Summer is high. Things kind of slow down a little bit between Labor Day and Columbus Day, pick back up for Columbus Day. We have some pretty incredible fall foliage up here in New Hampshire. So we get a lot of visitors during that season, and then things taper off until you hit the Christmas vacation ski week. So as we looked at this chart, we found that there were several windows that we felt this would be a viable alternative. So the two potential closure windows that were included in the contract are shown here in green. They spanned a time from March into mid-May, and then a couple of weekends between the Labor Day and Columbus Day weekends. The other provisions that were in the contract allowed for alternating one-lane traffic with a temporary signal, and certain operations were completed under that traffic condition, such as the pile driving You'll hear more about that later, but these sections between January and February vacation, and the potential closure window, as well as this period in the fall, were all identified as acceptable timeframes for the alternating one lane. One of the other big considerations that we had was looking at our detours. So how did traffic actually get around during closure weekend? And because of this location on really more of a regional route, we were really lucky. We were able to divert Route 16 traffic, which would normally travel here, diverted them on state routes, which is our typical practice. And it's actually about the exact same length, I think within maybe a mile of one another in terms of distance. So for those regional travelers, there was very little impact. New Hampshire 25 is this route. And so they were rerouted down. I think this added about 4 to 5 miles to that trip, again, for a regional traveler. One of the big advantages to this particular location, it's a little hard to see here, but there's a little purple line here, and that is actually a local road that paralleled Route 16 in the project area. That was open and available to local traffic that knew about it. So that really eased the local community's concerns about this closure. Other benefits for this particular project location, it's located equidistant from 3 area hospitals. So no matter which way you went, it was about the same travel time. And it was also located in a place where there were local fire stations and emergency response within the Ossipee community on both sides of the closure. And those are represented by the little red Fs on the plan. So ultimately, when we pulled together the 6 alternatives, the diversions to the east or the west, the new alignments to the east or the west, we actually had like a half and half, 1 diversion, 1 new alignment, along with the slide and bridge construction. That was really a clear winner. The wetland impacts, while we did permit some temporary wetland impacts on that eastern side, they are temporary and they'll be restored at the end of the project. The floodplain changes, there really are no appreciable changes. We maintained the clearances and actually improved them by slightly enlarging the bridges and removing some piers. Right-of-way impacts, again, those are all temporary. So that was great. We can turn those back to the property owners. There were no structures or residences or businesses impacted as part of the project. The highway alignment was able to stay where it was, which was the ideal place for it. And we estimated that we saved about 1 construction season. And from a preliminary cost savings standpoint, we estimated a savings of about $2 million over having to construct that temporary roadway and temporary bridges. So the approval to move forward with this alternative was gained right at the end of 2015. And then from there, we went into the design. This is a quick plan overview of the Bearcamp Relief Bridge. The new bridge is 170 feet long. It's a 2-span semi-integral straight steel girder bridge. This was the one that we sort of affectionately referred to as the test bridge. It was not required to be installed first, but we sort of thought that because it was over dry land, it's the smaller of the 2, it doesn't have a skew, that this would be the one the contractor would likely pick to do first, and that was correct. This one was completed in September of 2019. And then this is a plan just showing the Bearcamp River Bridge. The new bridge here is a 410-foot long, 3-span semi-integral steel bridge. So this one went from 5 spans to 3. This bridge was completed in October of 2020, and it did have a few additional complexities, both being over the river. It has haunched girders. It also has a slight skew. It's a 16-degree skew, but we were able to move those piers out of the river channel itself. So that was ultimately a benefit for this project. And with that, just sort of my time with the project was about the time we gained approval that I was promoted within the department to the position of project manager and out of bridge design. And at that point, we brought on McFarland Johnson to do the actual design of these bridges. So with that, I will turn the presentation over to Sam White, who will share a little bit about the design.
Thank you, Jennifer. I'd like to start the design considerations discussion, acknowledging the design standards used for both of these bridges. Both structures were designed in accordance with the 7th edition of the AASHTO LRFD Bridge Design Specifications, which is our national standard. The AASHTO LRFD guide specifications for accelerated bridge construction served as a resource during design, but were fairly new at the time of design and came out in the design process. The guide spec helped determine some of the forces induced by sliding the bridge. Construction submittal requirements which we incorporated into our special provision for the slide, and it provided good commentary on layout control and tolerance considerations for delivering the bridge to their final location. And lastly, the NHDOT Bridge Design Manual was utilized for state-specific design requirements. These next few slides are going to provide an overview of the replacement structures, give you a sense of more detail of what was built. Here's a typical section of the superstructure. Both the relief bridge and the river bridge are steel plate girder bridges with an 8-inch composite reinforced concrete deck. The out-to-out width of the superstructure is 37 feet, which provides roughly, well, it does provide 2 12-foot travel lanes and 5-foot shoulders. This image is a typical section of the piers for both structures. Both structures utilize 30-inch diameter concrete-filled pipe piles. And one detail I'd like to point out with the typical section that we have here on the right is that little notch or recess up near the top, which seems like a small detail, but was something that we built into the project to provide additional head clearance between the seat and the girders. And that was to provide space for pancake jacks to be used to lift the bridge for future bearing replacements, but additionally for vertical jacking operations during or after the bridge was slid into place to remove temporary slide components. This graphic is an elevation view of the piers. Each pier utilized 4 pipe piles that were located based on the existing bridge constraints. And there will be some more graphics later to help illustrate what we mean by those constraints. To facilitate the slide, the top of the seat needed to be kept level so that temporary slide support systems could be in place to move the bridge. And what you will see across the top is anchor rod sleeves that were used to keep the seat clean. So those sleeves allowed anchor bolts for the bearings to be post-installed after the slide. And then another component that is a little specific to the slide is that the cap, you'll notice the cap is a bit wider, the pier cap's a bit wider than the existing or the proposed superstructure. And end caps were detailed to prevent debris buildup on those flat sections. And those were installed via additional anchor rod sleeves after the slide. This typical section shows the semi-integral abutment detailing utilized, such that the back wall came in as part of the bridge slide. You'll also notice here a similar notch on the front face of the abutments that also served for vertical jacking purposes in the final condition. And this detail shows an elevation of the abutments. The proposed abutments located behind the existing bridge abutments were detailed to be precast with pile voids and a central closure pour, as shown in the detail. The idea during design was that these would be installed pre-roadway closure during the time periods Jennifer previously mentioned, where one-way alternating traffic would be allowed. This meant the piles and closure pour layout needed to be coordinated between the existing roadway geometry to allow for the maintenance of the traffic. So essentially, we couldn't close Route 1625 with installing any one of these precast pieces, or the piles for that matter. Now moving into some more of the design considerations specific to the lateral slide. 4 major considerations were the closure duration, moving the bridge, working around traffic, and the existing bridge constraints. The central focus of all of these that we had in mind during development of the plans were to provide the contractor as much flexibility with our detailing as possible so that they could come up with a solution that that fit them. And keeping with that closure duration, the contract roadway closure duration was 84 hours for each bridge, and precast elements were used for components that could not reasonably be installed during the roadway closure, or as part of the roadway closure. These images show the precast wing wall piece that were detailed to be placed on the abutment ends after the bridge was slid into place. And the idea here was that they could just be simply placed on top of that abutment stem, thus completing the wing wall installation and allowing for expedited backfilling to keep that process moving after the slide was completed. This graphic depicts several design considerations associated with sliding a bridge. Different positions. So one thing you don't really consider on a typical bridge is moving bearing locations. And as part of sliding the bridge obviously changes position over the proposed foundations. So that was a consideration that needed to be thought out during design to make sure at any one time pile capacities or cap capacities didn't get exceeded by moving the bridge at various locations. And in addition to that, any slide frictional forces that be imparted on the foundation. And for this project, the slide friction was limited to 15% static coefficient of friction. This image is a close-up of the vertical jacking operations needed to remove the slide assembly and install the final bridge bearing assemblies. In the foreground here, we have a jack sitting in the notch that was detailed as part of the abutment design to allow for that more head clearance. And directly above that jack, which is a little bit tough to see, is an additional stiffener that was detailed with the steel girders. And since the seat needed to be kept level to facilitate the slide, the beam seat, the bridge cross slope needed to be accommodated via varying thickness sole plates over the bearings, and that's the kind of meatier plate you see over top the bearing. Those varied in depth to form the cross slope. And since the location of the new bridge coincides with the existing, new foundations needed to be detailed around the existing bridge. And these photos show how the existing bridge dictated the location of the proposed piles. The piles needed to be installed through the existing deck and had to be spaced around the existing beams. And in that picture on the right, you see a hole that was cut through the deck. And Jim's going to have some better graphics for how that was all completed in construction. And another important consideration is vertical clearance tolerance between the proposed substructure units and the existing bridge, and why careful attention is needed for that during design to avoid construction complications. This picture shows the proposed foundation in relation to the existing superstructure at the relief bridge. This image is of the relief bridge just prior to a slide, which further highlights some of the site constraints when considering during design. The green rectangles shown are the location of the existing foundations. The proposed foundations were located to avoid these, as the existing bridge needed to remain serviceable during construction. And the goal here was to provide a hydraulic opening that mimicked the existing bridge, as Jennifer previously mentioned. And while this image just shows the relief bridge, similar considerations were necessary for the river bridge. And now I'm going to hand it over to Jim to discuss the construction aspects of the project.
Okay, so this first slide shows an overview. And at this point, you can see that we're looking at the old bridge, of course. You can see that the piers, both piers, the new piers have been built under the old bridge. You can't see the abutments, but they are underneath these patches in the road. They're already built. And the temporary support for the new superstructure, 2 of them are done. This abutment A is done. Pier 1 is done. There's driving piles for Pier 2's temporary support. The other thing to note on this slide is the utility lines, which have been relocated. We did some additional clearing, relocated utility lines well out of the way. At this point, it looks like just extra space, but you'll see soon that we used all of the available space. And in this is showing driving one of the first piles This was at the relief bridge, and it's one of the outboard piles. So as Sam said, 4 piles per pier, 2 outside the existing bridge and 2 right through it. To do the ones through the bridge, contractor first cut a square hole in the pavement, had 1-inch thick steel plates and some shims to put back over the hole. So those square holes were all cut ahead of time and the plates put on. And then as we get closer, they'd pull them off, cut the round hole in the concrete, and then cut the rebar out. The top right shows a template sort of that they set in there to guide the piles as they're being driven. The holes, and somebody had the good idea, let's put in some drop-in anchors to really hold this thing tight, but they just rattled out and it really proved unnecessary. There was also a frame at ground level to guide the pile. And because of the length, this bridge these piles are 180 to 200 feet long. So there's 60-foot pieces of pile welded together, and the plywood here is just to shield the people's eyes from driving by while the guy was welding. And you can see this point, you can see the traffic signal in the background. We're under alternating one-way traffic. And here we're driving a pile, and there was a lot of discussion during design about, a lot of concern about vibrating a pile through a red listed bridge deck. But what we really found when we get out there was that we felt a lot less vibration standing on the bridge from this pile driving than we did from trucks driving over it. And so it was really less of a concern than we had anticipated. And because of the scour depth, the theoretical scour depth, which were 40 feet, the top 60 feet of each pile had to be filled with concrete and a rebar cage. In most cases, a soil plug during the pile driving, but in some cases that plug formed a little too high up, so we had to use an auger. That's what this photo is of, an auger, to remove some material to get down to 60 feet was the level we needed to get down to for the concrete and the rebar. And this just shows some completed piles. These are pier piles at the relief bridge. Again, this made a really nice practice bridge, we called it, out in the field, because, you know, other than when during high water, you could walk all around it. You could move cranes around. You can almost reach up and touch the deck. So it's nice to have that. And this is just to show some of the tight tolerances, like Sam mentioned. Those new piers and abutments were right up tight under the existing bridge. This is a concrete pump reaching under to pour the concrete for one of the piers. When you're running the concrete pump in this configuration, some of you probably realize it's apt to plug. It was tough. You think about the guys who are up under there trying to put vibrators down in there and finish the top. It definitely adds a level of difficulty. And this is one of the abutments. This is actually abutment B at the relief bridge. And the way the plans were set up, we kind of thought that had planned on them precasting the abutments and installing them either during one of the periods where they could run alternating one-way traffic and then burying them, or maybe during the slide weekend. And that was the original intent of the contractor. But when they were doing these, installing the sheets for the cofferdam here, the superintendent, who knew that they had concrete slabs that could be used for a roof, asked about just casting them in place. And so they made a proposal, which we reviewed and approved. And so ultimately we built these abutments right underneath this concrete roof with traffic going over it. And you can see on the right-hand one, with guys working in there. Again, not the most comfortable thing, but no disruption to traffic at that point. And that was just one less thing to do on slide weekend. This, again, as Sam pointed out, no raised bridge seats. So the bridge could be slid over, and this is a good shot of the jacking shelf that was incorporated into the design. And then you've got the tubes for grouting in your anchor bolts afterwards. And this shows the pole beam, one of the pole beams sitting on top of one of the temporary piers. And so the bridge was actually built, the superstructure, on top of this pole beam right here. Underneath the pole beam are Hillman rollers, and they sit in this channel. And this channel will be extended right across onto the new substructure. And that acts as the guide when the bridge is pulled onto the new substructure. And this shows the wood blocking that was used in place of the permanent bridge shoes. They weren't allowed to have the permanent bridge shoes under it when they're sliding it. And then also note all the marks on the bottom channel. That we had those at each abutment and pier so we could keep track during the slide to make sure that everything was moving equally. These green blocks here, those are the Hillman rollers. This is a Hillman roller.
Hillman roller, upside down. As it rolls, the rolls are attached to the chain.
Some of you have probably seen Hillman rollers, some not. So we thought it'd be interesting to show how that works. It just rollers going around a center block held together by a chain. And then this is a little further along, the superstructure. These are the parabolically curved girders for the river bridge. And again, you can see it sitting on the pole beam. And the channel, you can't see the Hillman rollers, but they're right underneath there. Sort of conventional construction at this point for a little bit. This was a semi-integral bridge, both of them were. As well as the third bridge, which wasn't a slide bridge on the project. They're all semi-integral abutment designs, so the back wall, approach slab seats were all part of the deck. And this is just typical construction. You always want to dry run your screed, check rebar clearance, check proper cross slope, depth, all that. Did a lot of the precasting, was done right there on the site. You can see the green rebar, that's half of an approach slab. The long, thin things on the left are the sleeper slabs being cast. Again, that was done right on site by the general contractor. This is one of those wing walls, precast wing walls that Sam talked about, partially stripped. Those were a challenge for the bridge carpenters and the foreman and the resident engineer to sort that out. They came out really good. It was a very, very efficient design. And then this is starting demo. Demo is by far the trickiest and most dangerous part of the whole thing, both in terms of schedule and worker safety. This is a picturesque scene during the demolition of the river bridge, but I can tell you for those of us there, it was anything but relaxing because during the river bridge, the weather was terrible. It was cold, windy, rain. The poor guys in the full containment suits doing the cutting, their lenses kept fogging up, and then their filters would get plugged up because of the rain, so they couldn't breathe or see. And then they started to feel the electric current through their gloves because they were so wet. That wasn't a good time. And those of us watching the schedule and see us falling further behind, we were all trying to finish this one 12 hours ahead of schedule, like we did the relief bridge. The relief bridge, we had good weather. It went well. Finished 12 hours ahead. This is pulling over one of the piers. You'll see the flanges have been cut except for the closest flange to shore, which is left as a hinge, much like you're felling a tree. For those of you that done any cutting, so they just pulled it over in a nice controlled fashion and then went down and cut the rest of the flange. You can see everybody's in rain suits. They're all pretty cold and wet by now. This is pulling over another one of the piers. Now, I can tell you that pier right there, you could walk out to that. When we started the closure period, you could walk out to that and your feet would be dry. But it poured so hard that first night, the river came up and that thing was 30 feet from shore by the time we went to tip it over. This is the jacking setup, and you can see the hollow core jack, you can see the L bracket, and a Doughty dag rod going through. And so you pull till the jack is fully extended, retract the jack, spin the nut, and then go again. And that's the hydraulic pump that runs each one of the jacks. We had one at each site. We found that trying to calibrate them off of one just didn't work. So we had radio communication between all the operators. So the whole power for this slide is 2 single-cylinder electric generators. That's just a close-up of the pole beam, and that's half on and half off. And this is lowering. Lowering is much more difficult than pulling the thing sideways because you can only lower it so much at a time. So we replaced wooden blocking with these steel pipes and steel blocking for the second bridge, so we didn't lose so much in compression of the wood, and it made it go better. This is preparing the subgrade for the sleeper slab. The bridge still isn't quite slid over into place. And this is setting a sleeper slab. You can see the bridge still isn't put down, but you got to have things going concurrently if you're going to get done on time. And this is just some quality control to get things lined up. Compacting the backfill behind the abutment and in front of the sleeper slab. This is setting 1/2 of an approach slab. Once that's set in place, there's still a 3 or 4 inch space underneath that gets filled with flowable fill through holes. And we opened the bridges prior to membrane and pave, so we had to put ramps, fillets at the expansion joint. And this is a 4.5 minute video, time-lapse video. You'll see in the lower left, 10 o'clock, we reduced the traffic to 1 lane while we saw cut half the bridge. Sort of got a head start. And you can tell it's raining. Dots on the camera and everything, so including us. And it's cold in October. Again, I can't emphasize enough that the most riskiest part in terms of worker safety and time, which all relate to cost, is the demo of the old bridge. You never know, things are rusted. You know which has good support and what doesn't. You see by 10 o'clock at night, the deck was removed. We start with doing the steel. It was cutting that steel that really set us back on this bridge. We were ultimately able to finish on time, but not 12 hours ahead. When the sun came out, morale improved somewhat, but everybody knew we were behind schedule. So, and some people were still cold and wet too. There it goes. Again, this is probably the easiest part of the whole weekend, is sliding that thing across. Using the Hillman rollers, no less than 2% friction. Hydraulic jacks with the redag rods. A very smooth operation. Lowering, even with the steel blocking and pipes, still takes longer, but it was much better. You got to have spare stuff though. You know, seal blew on a jack. I guess covered with hydraulic oil, but they had an extra jack to throw right in there. And you see setting the sleeper slab. This end, there's similar operations going on in the other end. The closest one you can see better, the sleeper slab's there. They're going to swing up the approach slabs. Once those 2 halves are set, and you get the flowable fill under, you get it. There's a closure for in between those two halves, and that becomes the critical path because you got to get design strength before you can open the bridge to traffic. And for us, that was 20 hours to get the design strength. We had extra cylinders being tested at our materials and research laboratory. They were on standby. We were talking to them all through the night. And again, the bad weather prevented us from opening this one 12 hours early like we did the relief bridge, but it was still a success because it opened right on time and under budget. We had a lot of media attention. It's a big deal to the public. We had good buy-in, a lot of positive comments. DOT and contractor, everybody involved got a lot of kudos for this. And so this is just a summary. It was on time, under budget. When it was done, I think Jennifer covered a bunch of these things. And then that's what the river bridge looks like, and we should have time for some questions.
All right. Thank you for a great presentation. At this point, we are going to ask Paul Lives to moderate the question and answer period.
Yes, Torrid, thank you. And Jim, Jennifer, and Sam, really an interesting presentation. And Loretta, you got a good crew there. So anyway, we do have some questions that came in beforehand and a few questions that have come in afterwards, and questions are continuing to come in. So let's go ahead and get into it. We've broken them down into design, construction, and cost questions. And we'll start off with the design questions first. The first question came in beforehand. It was lateral slides have big footprints. How do you strike the balance between impacts to natural resources and impacts to traffic?
So with this project, like we talked about, because of the design criteria that we needed to maintain by constructing the temporary roadway and temporary bridges, we found that this using the slide didn't actually increase the impacts any over what we would have had, and we did get cost savings through utilizing the slide technology. This was a project that we knew we couldn't permanently close the road, and so the wetland impacts, were similar between all of the alternatives, and this one just led to temporary versus permanent.
Okay. Another one beforehand, what were the key factors that helped the decision making on selecting the type of project delivery method? I guess this was design bid build. Is that what you had? Yeah.
That is correct. That's New Hampshire's typical process. We've done a few design build projects, and we typically reserve those for the most expensive and most complicated. This project overall was pretty simple. The only part that was different or unique was the slide aspect. And in a lot of our research, most of the other states were doing a design bid build, so we just didn't see the need to go to a design build process for a project of this size or this type.
Okay. Was the lateral slide temporary abutment designed, or was it the contractor's responsibility?
That was part of the contractor's responsibility. The temporary supports and the slide system, the permanent foundations were part of the design process.
Okay. Did you have any takeaways from the Littlefields Bridge project in Auburn, Maine?
Yeah, so we were involved in that project, and I think for me, one of the big takeaways that it would have came up during construction submittal reviews was the slide methodology. On that particular project, they had used marine grease with steel on steel for the sliding, and that produced a much higher coefficient of friction. So something that that was noticed during it. In order to get the bridge to move, it produced a lot of pull on the Doughty dag bar before the bridge would actually move and enact in like a lurching motion, which for that size of bridge was perfectly fine. And on our specific structure being 410 feet long, there would be concerns with that and coordinating it between different foundation types. So the contractor ultimately chose a very, very good solution, and it worked very well. So that didn't come into play, but had things gone differently, that would have certainly been a learning lesson.
Okay. Do you have any feel for what the physical limitations of using the lateral slide method would be, specifically the length, width, and weight of the bridge or span?
So in our research ahead of time, we found that there are several very, very large structures that had been moved using this technique. I believe the project name comes to mind, Milton Madison. I want to say it was someplace in the central United States. It was a multi-span truss, very, very large, and that used this technique. There was another one in Washington State that again was 4-5 spans over, significant height over waterway. And so we figured if those states can do this on structures of that magnitude, that we could surely do this with the 400-foot. So there weren't any limitations that we ran into or found as part of that design process.
Yeah, with the method that the contractor used with the Hillman rollers, the Doughty dag rods, the bridge sitting on a pull beam, the forces really weren't very great. I mean, you're not pulling on the bridge at all, you're pulling on the pull beams. It really only took, even for the bigger bridge, about 18 tons of pull at the piers and 9 tons at the abutments. The manufacturer, the Hillman rollers, said 2%, look for 2%. And when we did a test slide of the relief bridge, I did a bunch of calculations for using the jack pressures, and we were running around 1.8%. So.
Okay. There was a question about what was the weight of the slide and span of the bridge.
The relief bridge was 3,000 tons. There's 285-foot spans. And then the river bridge was 3,500 tons. And obviously it was 3 spans, 217-foot approach spans, and 176 main span.
Okay, here's a question that says, how does digital delivery and information modeling technologies, specifically software, takes the place of maybe education and research?
Well, we're pretty conservative up here in New Hampshire, so we have not started using any sort of digital delivery or bridge modeling. We're still kind of doing everything a little more old-fashioned, calculations, drafting. So I don't know where that may fit in the future here.
Okay. There's a couple questions that came in beforehand. I mean during your presentation, and the first one is says in your options, it said, did you consider maybe staged or phased construction to maintain a closer alignment to the existing and also to remove the need for a detour? That'd be building one half and then the other half of the bridge.
Yeah. If you'll recall, this is a 6 girder system. So with the well, I don't have the slides up. So with the metal grate deck on one side and no central girder, you were only left with probably about 8 feet of actual concrete width to run traffic on. So that was not deemed feasible in this location because of the width of the existing structures and the way they were constructed.
Okay. Another question came in during your presentation. It says, did you really need the haunch girders from a fabrication standpoint? There was a question there. They look real nice.
Need? Yeah. I'm sure we could have designed a straight girder. I don't know if that's something you ever looked at, Sam. We kind of made that decision before you.
Yeah, there's a few, maybe even an intangible benefit to it. One of it being that the haunch actually lets you set that pier cap a little bit lower and provide some more vertical clearance between the existing structure during construction. So that is certainly a benefit of it. Also, this is a high recreation use area, so that aesthetic component to it was certainly appealing during design. It didn't necessarily add much of a residual conflict or added what's the word there, difficulties during the slide. There's a flat spot that you can't really see that was over widened at the belly of that haunch over the piers to provide more space for the vertical jacking operation.
Okay. Final question here, I see, on design was, what was the most challenging design component in preparing for a lateral bridge slide?
I would say maybe not so much of any one particular component, but more like specific bridge component, but more of the weekend closure aspect in and of itself. So developing details and always keeping that in mind that you're trying to put this in a weekend. So you need to afford the contractor as much flexibility as possible to let it suit their means and methods, introduce precast elements where possible. That's kind of where that jacking shelf made its way in, was just trying to minimize the amount of temporary works or additional temporary works that needed to be constructed.
Okay. We've got a whole bunch of questions that are coming in, so we'll try and go real fast on these pre-webinar questions. It says, how did the New Hampshire DOT mitigate the risk that the contractor may fail to complete the bridge slides and construction times allowed?
So probably the biggest thing we did was we required a detailed bridge slide plan and calculations for review and approval. Some of the components of that, it required a mandatory test slide, a mandatory hourly schedule had to be submitted for the closure, had to be submitted, a detailed slide and temporary works drawings and calculations. So that's probably the most important thing. He allowed, multiple closure weekends to give the contractor some flexibility in scheduling, because there's a lot of things that have to come together, a lot of subcontractors and suppliers and, weather, that sort of thing. But the most important thing is that detailed bridge slide plan and submittal.
Okay, that's very good. There's a bunch of sliding questions. The first one here was, can you discuss the sliding and jacking system methods used to keep the bridge in alignment and issues, lessons learned? You kind of covered that in your presentation. I don't know if you want to add anything to it.
No, not really. It's, it's controlled in one direction by those channels that the rollers were running in. They're bolted to the top of the new structure. And then in the other direction, it was controlled. All the operators for the jacks, for the pull jacks, had radio communications, and somebody was monitoring those little marks on the channel to make sure we're staying in alignment in that direction.
Okay. And then what methods are used to ensure that the portion slid into place is secure and it can resist final condition loading?
Well, in the end, Sam can chime in, but in the end, it's really a conventional design. Once it's set down and the anchor bolts are placed and grouted, it's our conventional design.
It's like any other bridge. Yep, just anchor bolts through a bearing.
Okay. And there was a question here on construction about what is the key lesson learned during the construction and installation of the bridges? What would you say was the key one?
Yeah, it's hard to say the key one. I had a key couple. One thing that we hadn't talked about yet was the road closure and detour issue. Lesson learned on the first one is we didn't have the signing we needed to get people's attention on southbound, because we couldn't close the road at the closest intersection because there's businesses and residences past that. So you had to have a way for traffic to come through, yet to be aware that they could only go 1.5 miles. And we improved that for the second one with larger signs set up. We already spoke about the steel blocking is better than the wood blocking when you're dealing with that kind of weight, just due to the compression. And the partnering aspect is huge between the DOT contractors, subcontractors, consultants. Everybody's got to be on a team.
Okay. All right, let's look at some cost questions real quick, and then I'm going to let Jugash take some of them. Can you provide a discussion related to contractor claims and any basis for it?
There were no claims. Both slides were completely successful. And I always say, as a construction guy, it's not completely successful unless it was successful for the contractor and the DOT. You know, if something hadn't gone well and there wasn't a team effort to deal with the problem, then we might have had a claim, but there were no claims.
Okay, Jim, good comments. What were the schedule specifications and how many bidders were there for the project, and how did the bid compare to the estimate?
You want to take that, Jennifer? I can. You know, there were 3 bidders. There were what, 2.6% between the A and B and 7% between the B and C bidders.
Okay. All right. That's good. I'm gonna, this has got most of the questions that came in up until we started the question and answers. I'm gonna turn it over to Jugash and let him pick up the questions that came in during the Q&A session. We got a bunch of questions. Jugash?
Thank you, Paul. Thank you, Paul. I have a handful of questions that came in. First one is asking what kind of backfill was used during the closure? Were there special requirements?
There really wasn't any special requirements. It was a granular backfill material. That approach slab was designed as a bridge, essentially. So the backfilling didn't have to be super strong, but we did do our normal compaction, and we used crushed gravel.
Okay, thank you. Next question, any reason why the approach buildups did not occur sooner in the closure schedule?
It was more just that they would be in the way. You can only have so many people in place at one time. The bridges were being removed from the middle to the ends, so you had to be excavator and loaders getting on and off, and it was more just a matter of room.
All right, thank you. Given weather events, were any claims submitted by the contractor related to the impacts?
No, they knew going in that there was no allowance for weather in this. We all had our raincoats ready.
Okay, good, thank you. Any penalties or rewards for late or early finish?
So there was a $4,000 an hour incentive disincentive for both of these. And as I said, on the relief bridge, they finished 12 hours early, so they got $48,000. And on the river bridge, they finished right on time, so there was no incentive or disincentive paid. There was a maximum incentive of $96,000 per bridge written into the contract. There's no limit on the disincentive.
All right, thank you. Next question, did they consider sliding the old bridges out to perform demo while sliding the new bridge in?
The contractor did not really. We did. During design, we talked about it a lot. I honestly thought on the bigger bridge that they probably a contractor would slide out the main span. They would demo the ones over land and maybe slide out the main span, but this contractor thought he could do it within the time frame and not do that. And so he would have everything done at the end of his 84 hours and he wouldn't have to go back and do more demo. He was right.
And that is part of what played into the amount of space that we acquired for temporary right-of-way, and that utility shift. Jim's very first slide showed that they'd been moved over away from the road, and that was intentional on our part to give the contractor that flexibility to slide it out if they so chose.
All right, thank you. Next question, how extensive were the details that were provided in the bid plans for the lateral slide?
The details were mostly, the detail that was included in the plans, so it was mostly schematic, showing what our concept or our vision was for it. And it's more specific to the specifications. The other limit that we placed on it was the friction force that could be imparted from the slide to our proposed foundation to limit those substructure forces and pile forces, which the method the contractor ended up selecting was a very good one, and the way that it resolved its forces resulted in no net force on the foundation due to the slide.
Thank you, Sam. Next question, how are the fixed and expansion bearing arrangement at the abutments and piers?
On the relief bridge, the pier was fixed and the two abutments were expansion. On the river bridge, both piers were fixed and the abutments were expansion.
Okay, thank you. Next question, what provisions were made to accommodate thermal movements in the longitudinal direction through the construction duration, from construction of temporary supports to slide in?
There really wasn't any. That the supports that they were, the temporary piers they were on, because those piles were 150 to 200 feet long. There's a lot of flexibility there. But that's it.
Okay, thank you. Next question, I don't know if this is valid. It says asking any limitations you guys found regarding heavy skewed bridges.
No, I don't think so. As long as the abutments are parallel and the piers are parallel.
Right, that's what I thought. Thank you. Next question, may I ask why the integral abutment system was not used for this location? Was it due to the length?
I think the primary purpose would have been more so that to jack it vertically and get that whole full integral connection formed within an 84-hour closure. That may have been a bit much and ambitious for our closure duration.
Okay, thank you. Next question, is steel used in this project category 5 or category 3? Not sure.
There's a few steel elements. I know if it's in reference to the pipe piles, it was grade 3, which has a higher yield strength, which we did utilize. I don't know if it's in reference to that.
Yeah, it must be. Okay, thank you. Next one, who did the slide design?
That Tom Densford did that. Well, he was the engineer of record for it from Stantec.
And that was done by or contracted by the contractor.
By the contractor, right. That's right.
Okay. I am up to my time limit, and there are a few outstanding questions which we will answer online afterwards. Thank you so much for your answers.
Thank you for having us.
Thank you.
All right. Okay. Thank you all for a great presentation. And this concludes our webinar. I'd like to thank all the speakers for a great presentation. And also just remind you that the deadline for submitting an abstract is February 25th. And Loretta, Jennifer, Sam, and Jim, I hope that you guys will consider submitting an abstract for the 22 conference, which will be in Miami, Florida. And again, also with the new opportunities that is coming up related to the infrastructure bill that was passed November 15 of last year. And so if any bridge owner or consultant see an opportunity to work with ABC UTC, we will be delighted to work with you. So again, on that note, we again thank all our speakers and all our audiences to be with us today, and hope to have you with us again next month. Okay, bye-bye.